My name's Emily, and this is our Static Truss Multimedia presentation. The other members of our group are George, Shaylin, Hunter, and Adam. So we decided to go with a truss analysis for our project, and this is the bridge that we chose to analyze. It's located in Paso Robles, California. We thought it would be cool to do something nearby. And also to increase the complexity, we added loads on the bridge, and that is shown in the free body diagram.
Okay, like Emily said, we added 3 loads. Each of them are 5,000 newtons or 5 kilonewtons. And we put them, and well, you can see we labeled all the points with them at E, K, and Q. And we put them at these specific points because if you look at the truss, it makes the entire thing symmetrical, which is really nice, as you'll see later on. So the first step to solving the truss is to figure out AY, TY, and TX. So for this, we're just going to take the whole truss, and to get AY, I took the moment about T and set that equal to 0, and that let us solve for AY. And since this truss is symmetrical, we know that AY will be equal to TY. So AY will be the same as TY. And so now we can start solving for the actual truss itself. This is the tedious part, which you just solve point by point until we get to the more complicated bit in the middle. So I started at point A, sum about the forces in Y and X, and that from there I was able to get AB and AC. And you can see there the C and the T next to it. That means AB is in compression and AC is in tension. This is important because it tells us which direction the forces at each point is pointing. So after point A, you sum it about point C and then point B, and that lets us get BC, CE, BE, and BD. And one thing you can note is that BC is a zero force member, which you technically don't have to solve for, because if you look at point C, there's nothing besides BC pointing in the vertical. Now I just moved it over one more step to the right, and we're going to sum points about E and D. This is a similar thing. You just sum up the forces in the X and Y, and through this we can get EG, DE, DG, and DF. And if you notice a pattern, all the horizontal components on the top are in tension, such as BD and DF. Or not tension, I mean compression, and all the ones on the bottom are in tension, which is just how the bridge is deforming. It's just an interesting little fact that you can notice throughout the truss. And then just move it one over again. It looks really similar because it's basically the same shape, but you just sum the points about G and F in the, or the forces G and F in the X and Y direction. Through this, we can get GI, FG, FI, and FH. And then the next one is where things get really complicated. In this one, I had to split the truss up because if you look at point I, we don't just have one force or two forces in the X and Y direction, we have 3 in each. So for that, I had to set up 3 equations, which one was force in the X direction, one was force in the Y direction, and then the third one, I decided to do a moment about G, because then I could get rid of any moment caused by IK, because it's pointing the same direction. You could do the moment about pretty much any point, but I just chose G basically randomly. And so you can see all the numbers down there. Those are my 3 equations. I manipulated the Fy equation to just H in terms of Hi and Ij, and then I plugged that into the moment of G equation, which also only had Hi and Ij, to give me Ij, and I could use that to solve for Hi and Ik. This was the complicated bit of the whole thing. And finally, we're back to simple stuff. Since we know Hi, we only have one unknown in each direction. So you can sum about the point H in the X and Y direction to get HK and HG, not HG, HJ. And the final value is JK. And then I just summed the forces in the Y direction about J, I think. And we only needed to do this half the truss because, as I said in the very beginning, it is symmetrical, which is really nice because we only have to solve for half the truss, and we can set the other side of the truss, all those forces, equal to the forces on the first half of the truss. And so here's all the values that I just took from all the previous slides and put them here. As you can see, we do have two zero force members, that's BC and RS, and all their members are there. Some patterns that I noticed was that all the horizontal ones along the bottom are in tension, which I mentioned earlier, and all the top ones horizontal are in compression. And another thing is, as you get more towards the center of the truss, the forces in each member tend to increase, which makes sense because they would be experiencing more load. And that's the workout problem.
All right, so now we're going to get into the concept questions. This first concept question that we came up with is how would the truss of the bridge support a moving car as it drives along the bridge? So essentially, while a car is driving along a bridge, it is a distributive force that's acting downwards on the bridge in the truss. To solve for distributive force, we can locate the centroid of the vehicle and then assume that it would be a single point force acting downward through the centroid of the vehicle. So as it moves along the bridge, basically at any point in time, there will be a single point force acting downwards at a position in the bridge. So for any given point in time, you could solve for how the truss is supporting the car at that specific point.
Here we have concept question number 2, and it's if a car takes out a member of the truss, how will this affect the overall distribution of loads? If the car managed to take out the zero force members on the bridges BC and RS, then the overall loads applied to the truss would be unaffected. However, if the car took out a two force member and then the weight-bearing members on the bridge, this would cause the bridge to have an uneven distribution of forces trying to support the 5,000 Newton loads from the bridge that we have from our original problem. In conclusion, this would cause the bridge to fail in supporting the loads and potentially collapse.
All right, so this next concept question is very conceptual, a little out of reach of like the methods of solving that we've learned in this class, but it is interesting to think about. So imagine like a heavy rain creates a flood, and the flood is pushing, like the water level rises to the level of the bridge, and the water is then pushing on the side of the bridge. We think about this in terms of dimensions. This adds another dimension to analyze. Initially, we're just looking in the X and Y direction of the truss, where when we add the water, it would be in the Z direction. So it had a third dimension to analyze. And after thinking about this, I kind of just came to the realization that you could split this up and then solve for the forces acting in the YZ plane, essentially how the water is pushing on each member of the truss. And then you could also solve for the analysis in the XY plane, such as what George walked through. And then you could sum these forces that are acting in all three directions. And if you were given the loads that would cause the truss to fail at like some magnitude, then you could compare that to these two different plane analyses and see if the flood would cause the bridge to collapse by force.
All right, and the final concept question, which is question number 4, essentially states if there was a traffic jam on the bridge, including 2 cars weighing 5 kilonewtons each on the right side of the bridge, and 1 car and 1 truck weighing 5 kilonewtons and 7 kilonewtons on the left side, how would this affect the forces of the members that the members are countering? Essentially, what this question is asking is, what if we applied an uneven distribution onto the bridge, which is already evenly distributed according to the free body diagrams and workout problem that we solved. Essentially, what this concept question is trying to get us to understand is what would happen to the zero force members and the rest of the reactions from all of the members if 12 kilonewtons were applied to the right side and 10 kilonewtons were applied to the left. What we came to the conclusion of was that in this situation, the uneven distribution of loads would cause some members which were previously zero force members to become members supporting loads. Furthermore, since these cars and truck would only result in forces acting in the y direction, we can conclude that the reaction at Tx would still remain 0, as we already concluded in the beginning when we first worked out this problem, that the Tx reaction force would remain 0. The cars and truck on the bridge would overall cause members that were previously equal in our original problems to instead be taking on different forces, and therefore the members on the left side, which are taking more force than the right side, the left side is taking the 12 kilonewtons and the right side is taking the 10, the left side would be taking on more weight, and therefore there would be more stress applied to those members in the situation. And that's the end of our concept questions and presentation.